Hello everyone, thank you very much for tuning in to this presentation today. It's a pleasure to be speaking at this Applied Energy Symposium, so the virtual version. And today I'm going to be talking about the demonstration of a 25 kilowatt dispatchable solar power system called the CSPond, or Concentrated Solar Power on Demand. So this was a very large collaborative project between people really all over the world, but mainly researchers that were at MIT and Khalifa University in Abu Dhabi. So the people listed here are just a few amongst a very large team of passionate people working on this project for several years. So if we look at the energy reserves here on Earth for both finite and renewable energy resources, the sun is really looking quite good in terms of energy available. So here you can see this shows you the reserves in terawatt years, and the little corresponding bubbles show the relative scale of each energy resource. So for both renewable and non-renewable technologies or energy resources. Now, despite having so much solar energy available, the problem with the sun is that first, it's dilute, so we only have 1 kilowatt per meter square, and it's intermittent. So every energy resource is going to have its trade-offs, and this is the situation that we're dealing with when it comes to solar energy. So this is where concentrated solar power comes in. So a lot of you are already familiar with concentrated solar power, and some of you may not be. So it's a technology that has the potential to eliminate the problem of intermittency in renewable energy. So the way that it works is you have this big field of mirrors on the ground that concentrates natural sunlight hundreds to thousands of times and focuses it onto a receiver, which in this design is located at the top of a tower. So this is really the state of the art in concentrated solar power technology at the moment. So the receiver consists in arrays of tubes with a fluid circulating inside. So the natural sunlight can heat the tubes and then heat the fluid that circulates inside. So this can be a molten salt and can be heated to temperatures from 500 degrees C to 1000 degrees C, and it's then used as a heat source for power generation. So we can have a closer look at how this specific tower technology works in terms of power plant operation. So the salt exits a cold salt storage tank at 290 degrees C, and it's circulated to the top of a tower through the receiver, where it's heated by this concentrated sunlight. It then circulates back down to a hot salt storage tank. So in this case, the hot salt storage tank is at 565 degrees C. And so here, as I mentioned, we're operating with molten salt. So then it passes through a heat exchanger where it converts water into steam, which is then used to drive a steam turbine and produce electricity. So we can extract at a constant rate to produce electricity day and night, and the volume of salt in the cold and hot salt storage tank are going to vary. So if you're producing excess thermal energy, then the molten salt in the hot salt storage tank is going to be increasing. So this is the concept of thermal energy storage, and is what allows concentrated solar power to eliminate intermittency in electricity production. So here you can see the state-of-the-art two-tank thermal energy storage technology. So this is, of course, sensible heat thermal energy storage. And so it's very cheap and simple in comparison to battery technology, and allows to dispatch our electricity 24/7. They also have, molten salts have a very large volumetric heat capacity, which is in fact similar to water, and it can therefore store a large amount of heat at very high temperature. Now, the levelized cost of electricity of CSP technology has been decreasing steadily every year for over a decade, as you can see here in this figure. So what we're seeing here is in 2010, this is the levelized cost of electricity, so 10 years ago for concentrating solar power. And then in 2019, we can see the cost has steadily decreased in 10 years approximately. And in fact, some record low costs down to 6 cents per kilowatt hour have also been reported. But nevertheless, CSP technology is still not really able to compete with fossil fuels, so this is where the range for fossil power, or even photovoltaic technology for that matter. And the main reason is CSP plants are still a very large capital cost investment, and so they're really expensive to make. So if we look back at our state-of-the-art solar tower technology, here we have the field of mirrors, so the heliostats are the most expensive components of the entire system. Now, the other problem with this technology is we have a receiver and storage technology, so these two tanks that require very high power pumping powers in order to pump the salt at very high flow rates to the top of a tower and then to these two storage tanks. So in order to reduce these pumping requirements, which will in turn reduce the cost because we'll also need less heat tracing, we would ideally like to combine all three into a simple single unit. Now, the other issue is that the max flux that can be tolerated by the receiver is limited by the tube material. So as you recall, this receiver consists in a bank of tubes, and this concentrated solar radiation irradiates the tubes and then heats the heat transfer fluid. So an alternative is to absorb this concentrated solar radiation volumetrically directly into the working fluid itself. So it's a self-healing surface that can tolerate higher solar fluxes and solar flux variations. So this brings me to the CSPond concept for concentrating solar power on demand. So in the CSPond, we essentially have a 3-in-1 CSP concept with volumetric absorption that essentially eliminates all the issues that we have with this tower technology. So the way that it works is concentrated solar power is beamed directly into a big open tank of molten salt where it's absorbed, this concentrated solar radiation is absorbed volumetrically since the salt is semi-transparent to solar radiation. Now the tank is divided into two sections by a divider plate. So above the divider plate is the hot heated layer and below is the cold layer. And I have a little animation here that illustrates how the whole system works. So during the day, this concentrated solar power heats the hot layer, and so that hot volume increases, and during the night we close the tank, so we close the aperture, and we continue to extract hot salt from the hot salt layer, except that this hot layer is now decreasing and the cold salt layer is increasing. So the CSPond concept was originally developed about 10 years ago at MIT, which involved the concept development and some lab scale experimentation, so a small lab scale CSPond prototype. So the idea was to have the single tank concept paired with hillside mounted heliostats, which has a single reflection to the lid of the receiver. So that was phase one. So here you can see on the left the design of the phase one CSPond demo prototype, and on the right you can see the hillside mounted heliostat optical design that was envisioned for the CSPond. So in phase two, this was in collaboration with the Masdar Institute Solar Platform in Abu Dhabi, which is led by Dr. Nicolas Calvet, and it consisted in building a demonstration prototype of a 25 kilowatt CSPond system. So for the demonstration, we integrated the system with our existing beam down facility, but as I just mentioned, a CSPond would not be limited to this optical configuration since beam down technology tends to be a little less efficient in terms of optical efficiency. So the tank installed is 1.25 meters in diameter and 2 meters in height, and it's filled with sodium potassium binary nitrate salt, which you can see here on the right, which is a view. This is a view looking straight down into the tank of molten salt. So the tank is made of 3 millimeter thick 304L stainless steel, and it's insulated with 2 concentric layers of pyrogel and rock wool. So the tank is then instrumented with 9 multi-junction K-type thermocouple rods of 2 meters in length, and they were sheathed in Inconel in order to avoid corrosion. So on the right is a top view of the tank, which shows the locations of these 9 thermocouple rods. Now, the divider plate consists of a 1.2 meter diameter by 30 millimeter thick welded 304L stainless steel shell, and it has 8 air chambers that are formed by 7 radiation shielding discs. So you can see these discs in this figure right here. So you can see the discs that form these radiation shields. And you can also see the hoisting mechanism for the divider plate. So you see the whole hoisting mechanism here on the left. So the idea for the divider plate was for the shell to be airtight, such that the poor thermal conductivity of air would insulate the hot layer from the cold layer, and then these internal discs would reduce radiative transfer from the top to the bottom of the divider plate. However, we did have some issues with salt penetrating inside the divider plate, which I'll talk about a little more later. Now, throughout the design process, we were very concerned about developing hotspots because we knew very little about the thermal fluid behavior of the salts, how the volumetric heating would be distributed, and if enough natural convection would develop to mix the salt. So in order to promote mixing, a mixing plate was added in order to create active mixing in the heated layer. So you can see the mixing plate on the right here. This is our mixing plate, and it's located above the divider plate and has its own hoisting mechanism. So it has these holes. Here you can see these holes, and it allows the salt to flow through the holes as the mixing plate moves up and down. And the jets that flow through that are formed and then promote mixing into the salt layer. Now finally, the tank was mounted with a final optical element, which is a 3D secondary concentrator, to increase the final flux that's delivered to the tank and to reduce the thermal losses. So it consists of a hexagonal cone with aluminum facets, and it was removed at the end of each day, and the tank aperture was closed at night in order to reduce thermal losses during nighttime operation. So the design and construction of the prototype took several years, a lot of cooperation, coordinating a lot of weekly WebEx meetings for people at opposite sides of the globe. So at the time we had people in California, in Boston, in Abu Dhabi, and I think in China. And there was a lot of sweating out in the desert was how this whole construction happened over multiple years. So one of our colleagues actually made several videos of the whole construction process over the days and months as it occurred. And so here you can see this was over the course of a day assembling the top collar and the deck platform. So you can see the tank already, and they're installing the top collar. And now we see the deck platform. And now another video of installing the insulation and the temperature sensors. So I really like seeing the position of the sun change during the day in this accelerated video. So meanwhile, while all of this construction was going on, there were several lab experiments that were also going on in parallel to the design and construction of the prototype. So in particular, we did a lot of experiments with respect to the salt properties. So we focused both on the optical properties of the salts and the thermophysical properties of the salts. So here you can see this is a custom setup that we developed from measuring salt, for measuring the salt's optical properties. So one key finding that we found was that although the salts are used in existing power plants up to 565 degrees C, when they're heated in these open atmospheric conditions, they actually start to decompose at a lower temperature, and they become cloudy and lose all of their volumetric absorption properties. So here you can see in this top image here, we have the regular binary nitrate. So this is a commercial salt provided by SQM at 400 degrees C. And then below it is what we see when we decompose the salt. So when we overheat it to 550 degrees C for 30 minutes, it becomes this kind of cloudy color. So the thermophysical properties don't change that much at this temperature, but the optical properties do change significantly, and it significantly changes the volumetric absorption. So this indicated to us that we couldn't go to very high temperatures. or as high as we would have liked to. And then the last salt that we also looked at were these binary chlorides of sodium potassium chloride, because these are salts that we're looking to for the next iteration, the next phase of the CSPond. Now we also looked at the effects of adding sand to the salt, since this is an open tank operated out in the desert. So we got a lot of questions over the years about sand entering the tank and getting into the salt. So the effect of these impurities on the thermophysical properties, and mainly melting and crystallization points, thermal stability, and specific heat. So these effects were actually found to be pretty insignificant when we added sand. So the effects of these impurities on the optical properties was also measured experimentally in the lab in the same setup. And what happened was that although the sand does have an effect on the optical properties in the short term, it was actually found that the sand settles over time, as shown in the figure below. So here we melted some salt in a crucible, added some sand, and just let it sit there for a little while in the furnace. And we could clearly see that the sand just settled to the bottom, and it had what remained suspended in the salt had a very negligible impact on the overall optical properties. Now, that being said, over time, it's possible that the tank will have too much sand settling at the bottom, and it will make operation a little more difficult. So eventually it may be necessary to add some sort of fibrous metal filter to remove the excess solid particulates from the salt. So here you can see the salt loading and melting process. So roughly 3.8 tons of commercial salt were provided by SQM and were added to the tank, as you can see here. So we did have some issues in the loading process because the salt spent a significant amount of time in storage, and because Abu Dhabi is in fact very hot and also humid and not dry at all in the summer. So the salt had caked into very large blocks. So the entire melting process, once we got everything mixed and eventually made a powder out of this giant caked block, the entire melting took approximately 4 days to complete, and it was done primarily with solar energy, so 80% solar energy, and then this was assisted by some electrical resistance heaters. So overall, it was estimated only 20% of the energy used to melt the salts came from external resistance heaters. So in order to accomplish the smelting process, what we did is each day we added more salts to the tank. So we added some salts, melted it with some solar energy, and then the next day we added more salts, melted with more solar energy, and so on until 4 days later everything was melted. So this was quite remarkable considering how reflective the salt appears to visible light. In fact, we did not do any optical experiments on the frozen salt, only on molten salts. So we did also look into methods for accelerating the melting process, such as, for example, sprinkling highly solar absorbing slags at the surface of the salt, which would eventually sink at the bottom of the tank once the salt was melted. But we didn't actually need to use them here since we had these resistance heaters, but it is something that we can look into in the future if we really wanted to achieve this without any resistance heaters at all. So overall, really, this was a huge success since it was the first time ever that anyone had melted salts exclusive or almost exclusively with solar radiation. And in fact, so traditional salt melting processes actually require fossil fuel fired melters in order to melt the salt. So this is a lot greener and simpler process since everything is done integral in the actual system. Okay, so now on to the experimental results, which is, of course, the most exciting part. So here you can see the temperature profile in the molten salt for a charge between 350 degrees C and 475 degrees C on June 22nd. So June 22nd is when this experiment was carried out. So here you can see I have temperature versus time of day. So the objective of this experiment was to gradually heat the hot salt layer at a uniform constant temperature of approximately 450 degrees C. So in this case, each curve corresponds to the average temperature at different depths as a function of time. So you can see here, curve 1, so this is located at the bottom, so this green curve is located at the bottom of the tank, so it corresponds to this location here, and curve 12 corresponds to this location right below the surface of the salt, so located right here. And so the height of the divider plate is progressively lowered throughout the day to control the temperature of the hot salt layer as we continue to absorb solar radiation. So once the divider plate and mixing plate reached their lowest position, which was at 1:10 p.m., the surface temperature was above the set point. So you can see here the surface temperature was slightly above the set point, which was 450 degrees C, as you remember. So the mixing plate was then moved rapidly through one up-down stroke at 1:12 p.m. And this very rapidly homogenized the temperature distribution. And we can also see one other phenomenon that we notice from these curves is that we can also see the thermocouples located below the divider plate that are starting to heat up. So we can see these lower curves. So this curve 1, 2, 3, we start seeing them also increase in temperature, indicating that there is some convection to the bottom layer. So here is again, for the same experiment on June 22nd, we can see this dashed line here. This dashed line corresponds to the divider plate position at the start of the experiment at 8 a.m. So during the day, as we progressively heat the salt above the divider plate, so this dashed line corresponds to the top of the divider plate, moves down, and it allows more salt to become exposed for solar heating until the divider plate reaches its lower position at 1:10 p.m. So we can see this curve is not entirely uniform at 1:10 p.m. So we can see this curve is kind of, we don't have a completely uniform temperature in our salt as we were hoping for. And in fact, this non-uniformity is worsened by the fact that the mixing plate is blocking some solar radiation from reaching the divider plate. So after the mixing stroke, we now have this temperature distribution here, so it's much more uniform until the end of the experiment. So we can also see once again that the bottom layer is being heated by conduction, because we can see these temperatures are also increasing throughout the day. Now this figure shows the cumulative energy stored in the salt mass over time. So this was estimated using the average temperature at each height in the salt. So we have energy in kilowatt hours versus time of day. So this trend is as we would actually expect, even before and after the homogenization with the mixing plate. So here we can see here is where the single mixing plate stroke occurs, and the energy still continues to follow a continuous trend in time. Finally, the last experiment that was done was this experiment that we call the uniform charging mode. So when the system is to be used to generate electricity only after sunset, the temperature of the hot layer no longer needs to be maintained constant while it's charging. So the receiver losses due to the exposed hot surface can be reduced by charging the entire volume from a colder state to a hotter state, rather than trying to keep the hot layer at some set point throughout. So even with no mixing plate motion, the gradient of temperature in the useful volume of salt is less than 10 Kelvin per meter. So you can see here I have, once again, temperature versus time of day. And actually in this uniform charging mode, all of these curves, so from all of these points from 8 to 12, they all almost overlap. And so the temperature is very uniform in these experimental conditions. So this actually suggests that natural convection was substantial enough in this case to maintain the salt at a relatively uniform temperature. And if the system is designed and operated appropriately, the mixing plate may not be needed. So some general conclusions and takeaways. The CSPond allows us to reduce the need of heat tracing that is typically required for tower and receiver piping. And this is because we now have this nice, simple 3-in-1 system. There's no need for high pressure pumps for cold salt transport to the tower receiver, very low parasitic energy consumption. The initial melting didn't require any fossil fuels, so we only needed solar radiation and a little bit of help from our resistance heaters, and it was accomplished in 4 days. There's no need to drain the solar receiver at the end of each day of operation, and we have a reduced susceptibility to thermal shock because the solar radiation is now absorbed volumetrically, so when we have variation throughout the day due to focusing and defocusing or when clouds pass, it's much less susceptible to shock because it's being absorbed over volume instead. Now, some lessons learned and some future work. So there were things, of course, that worked and things that didn't work so as well as we had planned. So in particular, if I look at, for example, the divider plate, the pros were it effectively blocks solar radiation from the cold bottom layer. The cons is it was not as effective as we had hoped at thermally insulating each layer. So that was one big issue that we had with this divider plate, and the motion is also manually controlled, meaning we do have this hoisting mechanism, but we need some user to actually control its position throughout the day depending on what temperature reading we have. So some future work would be to improve the thermal design and to improve the automatic control of the divider plate. Now moving on to the mixing plate. So the mixing plate did a really good job at providing some additional redundant mixing. However, it did block the solar radiation from penetrating to the divider plate. It was not as essential as we initially expected. So if we design the receiver and such that we promote passive mixing due to natural convection, we should be able to get away with it without it. And finally, this active mixing mechanism, so we have more hoisting mechanisms and all of this active mixing is an additional possible failure mode in the receiver. So it is something to consider. So future work involves implementing passive mixing inside the receiver. So how do we actually get this passive mixing? And as I said earlier on, I mentioned that the reason why we put the mixing plate in the first place was because we had a very poor understanding of the overall thermal fluid behavior. So that has changed in all the years since starting this project. We did gain some insight in the thermal fluid behavior inside the receiver. And so by doing some CFD and some theoretical analysis, we now have some models to actually predict the temperature distribution in the receiver as a function of time, and to actually predict what conditions give certain conditions that are favorable for natural convection. Now, one of the very important points to address here are the thermal losses, because as we know, we have this big tank of open molten salt that's open to the atmosphere, and so we do have thermal losses from this exposed salt surface at high temperature. And so, of course, the advantage of having this big open tank is that we enable direct volumetric absorption, but the downsides are that we have thermal losses, and also it's open to dust and sand from the surrounding environment. So future work involves integrating a solar transparent cover. So we did work on this in the lab, and we developed an insulating cover for this direct absorption molten salt receiver. So it's solar transparent, and it reduces thermal losses up to 50%. So it consists of these hollow quartz spheres that are floating around on the surface of the salt. And so the remaining work is to just actually deploy it in the prototype and test it under real solar conditions and not just in the lab. Now, we talked about the thermal losses, so thermal efficiency, but there's also the optical efficiency. So we can improve the geometry of the aperture, but most importantly, we can deploy the concept in some alternate, more efficient solar field and receiver configurations. So as I said, this was all tested and demonstrated in a beam down facility, which has 2 reflections. But the CSPond concept was actually developed with hillside mounted heliostats in mind. So that would eliminate one additional reflection, which would reduce the optical losses. And some final lessons learned, well, And future work, well, we also have continued prototype operation to assess the reliability and obtain some long-term data. We need some more materials testing, and we need to operate at higher temperatures. So this is something we're looking at for the future, is to operate with chloride salts, which are much higher temperature and would allow us to operate in using gas power cycles instead. So some acknowledgements. As I mentioned earlier on, this was a huge team. And I want to thank everybody who worked on this project with me. Questions?